Uh, so in this problem, we would like to disprove a well-known result. So the first one, let us start with the first one. There are two parts. The second part is very, very beautiful, the Borel-Cantelli lemma, but let's focus on the first one. The first one is, what we want to say is that if you have a countable decreasing, so you have sequence of measurable sets, okay, and we assume that the ENs are decreasing, which means that En plus 1 is a subset of En. So we want to say that the measure of the intersection of the ENs is exactly the limit of the measures of the ENs. This is true if they are all finite. Okay, so if we assume that after a certain n they are all finite measures, they have finite measures, then it's true. Otherwise, this is false. Okay, so this is false. Okay, in general. So why? Because we can take the ENs to be n plus infinity, the open interval. So we know that the measures of the ENs all is equal to infinity, and the intersection of all the ENs is empty with the measure 0. So this relation is valid, as we have seen before, if the measures of the limit or the limit of the measures is finite. If we assume that this is finite, then the conclusion is true. The second problem deals with the famous Borelli-Cantelli lemma. So in this case, we only have not disjoint, nothing, not decreasing or increasing. We just have a sequence of measurable sets, and we assume that sigma of the measure of the ENs is finite. Okay? And what's interesting is that the measure of the set, so we consider X set of X such that X belongs to En for infinitely many n's. So this set has a measure 0. Okay? So in other words, for almost all x, all real numbers, they belong only to finitely many what? ENs. So for that, let us consider the union of the EIs from n to infinity, and where n is fixed. Okay? So this one is going to have, is measurable. It's a sigma union of measurable sets. And we know that its measure is going to be less than sigma of this is by subadditivity, of the EIs from n to infinity. We don't have equality because we're not assuming that they are disjoint. Then what happened is that when n goes to infinity, because this is a converging series, and therefore if we let n go to infinity, this tells me that the limit of the measure of these sets from n to infinity, when n goes to infinity, is 0. Because that's the remaining of convergent series. Okay? So now, what's interesting is to see that either you use the continuity of M, the Lebesgue measure, or if you look at the set E, then we can show, in fact, that this set is the intersection of the union of the EIs from n to infinity, where n is greater than 1. Okay? Why? Because if x belongs to E, then we have if and only if, okay, for every n, okay, because it's infinite, uh, there exists uh, um, an n greater than n such that x belongs to En. Okay, so that's why you have this infinitely many of them. Otherwise, you will have only finitely many of them. So, of course, this tells me that this is for every n. Okay, uh, x belongs to the union of the ei's for i's bigger than n, which tells me that x belongs to the intersection of all the unions, okay, from n to infinity for any n greater than 1. So this tells us exactly what we want. And then we have the measure of E will be less than the measure of the union of the EI's from n to infinity, okay, for every n. And since this one goes to 0, as n goes to infinity, we know then this will imply that the measure of E is equal to 0.